No, you can't.
Sir,
you could
is
chat
it
to him.
visible?
Yeah, that's great. And Neha, if you've got a camera, if you could turn that on, that would be great. But otherwise, we can hear you fine. So please give us your talk.
So let me check.
Neha, go to the Zoom icon.
So is my screen visible?
Yeah, that's great. And we can see you as well.
Yes, sir.
All right, brilliant. Okay, please give us your talk.
So good afternoon. I am Neha Bisht, research scholar in the Department of Ocean Engineering and Naval Architecture, Indian Institute of Technology, Kharagpur, India. So the topic of my presentation is triad resonance of flexural gravity wave on uniform flow in the context of blocking dynamics. The outlines of the presentations are introduction to triads and flexural gravity waves, its objectives, motivation, literature review, mathematical formulation, results and discussion, conclusion, and references. Introduction to triads. What is resonance? When a wave strikes an object which is vibrating with some particular frequency, and if the frequency of the wave matches with the frequency of the object, then resonance occurs, and the corresponding frequency is known as resonant frequency. Triad resonance. The interaction of two propagating waves with wave numbers K1 and K2 may produce a wave with wave number K3 such that K3 is equals to K1 plus minus K2 implies omega 3 is equals to omega 1 plus minus omega 2. This is known as triad resonance condition. Here, if K1 and omega 1 and K2 and omega 2 satisfies the dispersion relation, then K3 omega 3 also satisfies the dispersion relation. What is flexural gravity waves? Interaction of gravity waves with thin elastic plates like floating runway and bridges generates flexural gravity waves which propagates along the elastic plates like floating runway and bridges. Of energy in sea wave spectra, and energy transfer among gravity waves plays a major role in sea surface evolution. Wave resonance is one of the primary energy transfer mechanism. Resonance condition can be found in case of capillary gravity waves, surface and internal gravity waves. In this study, an attempt is made to understand the formation of triads in the case of flexural gravity waves with current for understanding the spectral distribution of wave energy on the floating structure. The objective of my study is to analyze the formation of triads in the case of flexural gravity waves with uniform current, the dispersion relation for an infinitely extended floating plate covered surface in the presence of uniform current is derived, the role of following current and the opposing current on the occurrence of triad is investigated. Literature review. In 1960, Phillips discovered a mechanism for nonlinear resonant interaction between two or more trains of progressive gravity waves in deep water and demonstrated that resonance triad will not form. In 1964, Ball demonstrated the occurrence of class 1 triad resonance in two-layered density stratified fluid and developed the Ball diagram to study the triad resonance graphically. In 1965, McGoldrick studied the triad resonance exists in case of deep water gravity waves with the inclusion of surface tension, whereas recently Kosklos revisited the problem of Phillips 1960 and demonstrated that triad resonance can occur in deep water surface gravity wave in the presence of current. Myself with Susham and Professor Sahu and Professor Malin demonstrated the existence of triads in case of flexural gravity waves in two-layer density stratified fluid in the perspective of blocking dynamics. Basic assumption and schematic diagram. Here, the fluid is considered to be inviscid and incompressible. The flow is irrotational. Motion is simple harmonic in time with frequency omega. The floating elastic plate is considered to be homogeneous and isotropic and modeled using the Euler-Bernoulli beam equation with the inclusion of lateral compressive force. The mathematical model is formulated using linear water wave theory and small amplitude structure response. The velocity potential for the fluid domain is phi. This is the opposing current. This is the plate covered surface. Mathematical formulation. The governing equation is given by this. The linearized kinematic boundary condition on the plate covered surface is this. Euler-Bernoulli beam equation is taken to be this, where E is the Young's modulus, I is the moment of inertia, N is the lateral compressive force, rho P is the density of the plate, and D is the thickness of the plate. PS is the external force. So hydrodynamic pressure acting on the elastic plate. So PS is equals to this. Now, linearized dynamic boundary condition on the main plate covered surface will be this. The linearized plate covered boundary surface on the main surface in the presence of uniform flow will be this, and the impermeable rigid bottom and boundary condition is this. The plane progressive wave solution, the plate covered surface is assumed to be of this form. The phi is given by this equation. And dispersion relation for flexural gravity wave in the presence of current is given by this. If we take omega minus ku is equals to sigma, then the dispersion relation will be of this form or in omega form like this. Now for deep water approximation, 10 hyperbolic kh is equals to 1. So our dispersion relation will be of this form. Dispersion plot under deep water approximation. Here the dispersion plot for sigma k is plotted here. So we can see this is the blue curve. This is a blue curve sigma, and this is omega minus uk pink dashed line. And this is plotted for the plate covered surface with compression 0 and u is equals to -1. Here we can see omega minus uk intersects the sigma at 2 points A and A dash, corresponding to the wave numbers K0 and K dash. So in the subsequent discussion, we will consider only the positive wave number. So we will consider only the point A. Here in figure B, dispersion curve for K omega is plotted with u is equals to -1 and q is equals to 0, and which is a blue curve, and the pink dashed line is D dispersion curve for K omega with -u. And O is the origin. Triads in flexural gravity wave with current U is equals to -1 and Q is equals to 0. Here, we are going to use the Ball's diagram to demonstrate the formation of triads for U is equals to -1 and Q is equals to 0. This is the dk omega U with U is equals to -1. Which is originated with the O, which is originated from O, and this is the pink dashed curve, which is dk omega with -u. So taking a point on the blue curve A and shifting the origin of the pink dashed curve, that is the dispersion curve with the opposing current, to the point A. A is known as the shifted origin. So here we have shifted the origin of the opposing current, dispersion curve with opposing current to the point A instead of origin O. So ping dashed curve intersects the blue curve at point B, giving us one triad OA plus AB is equals to OB. So OAB is a triad. While in figure B, the dispersion curve with the dispersion curve dk omega u, which is a blue curve for q equals to 0 and u is equals to -1, originated from point O. The pink dashed curve is the dispersion curve with the with opposing current minus u, taking the shifted origin at point A. It can be seen that the pink dashed curve intersects the blue curve at point 3 for the higher value of the frequency. So here the three intersecting points are B, C, and E, giving us three triads OAB, OAC, and OAE. Now triads in flexural gravity wave with current U and Q is equals to 0. So here again, in figure A and B, the value of the compression is 0 and U is equals to 1. So the blue curve is the dispersion curve with the with U is equals to 1 and originated from point O. Now taking an arbitrary point A on the curve, on the blue curve, and shifting the origin of the same curve that is blue curve to the point A, and we can see this is with positive U and this is also with positive U, and we can see that the pink dashed curve intersects the blue curve at point B and giving us one triad OAB, OA plus AB is equals to OB for the lower value of frequency. Similarly, in figure B, the dispersion curve dk omega u is originated from point O, and this is the dispersion curve dk omega u originated from the point A instead of the O. So here the pink dashed curve is intersecting the blue curve at 3 points B, C, and D, giving us three triads OAB, OAC, OAD for the higher value of the frequency. This phenomenon this is not observed in the case of surface gravity waves with the current. Wave blocking. Wave blocking occurs when the group velocity becomes 0. However, the phase velocity may or may not be 0. Under the assumption of surface gravity waves having a plate covered surface, blocking occurs for two different frequencies, and near the blocking point, the wave crest increases in height, which leads to an increase in potential energy of the wave. Here, again, wave blocking is continued. So here we are taking the dispersion curve for the floating elastic plate without current. This is the dispersion curve for the variation of Q without current. This is the dispersion relation, and we are considering the deep water approximation. Now here we can see for the lower value of Q, that is Q is equals to root dg, we can see only one propagating wave mode is there, that is A naught. Now as we increase the compression, Q is equals to root 20 dg by 3. We can see here A is the point of inflection where the three root pulses. Now for the values between, for the compression value between Q is equals to this and Q is equals to this, we can see the with the increase of compressive force, the point of inflection bifurcates into two optima, that is B and C, which is known as the primary blocking and the secondary blocking. Here, no energy propagation will take place at these points. Now, within these blocking limits, B and C, three propagating wave mode will exist, A1, A2, and A3. Dispersion plot under deep water approximation. Now here we are considering the blocking case for Q is equals to root D and U is equals to -10. And in figure B, we are considering the higher value of the compression, Q is equals to 1.9 root D and U is equals to -1. Here we are taking the higher value of current, and here we are taking the higher value of the compression. So we can see with the increase in the value of the current, the blocking will occur, or either we can increase the value of the compression and the blocking will occur. So here this is the sigma curve, and with the sigma curve, yes, this is the sigma curve, and this is pink dashed is the omega minus UK. So omega minus UK intersects the blue curve at 3 points, A1, A2, and A3. These are the 3 points, 3 propagating wave mode. Similarly, here for the lower value of the current and higher value of compression, we can see omega minus UK intersects the blue curve at 3 points, A1, A2, and A3. Now we will consider these propagating wave mode Now we will consider these propagating wave mode for the formation of triads. Occurrence of triads within the blocking limit. So now we are considering the case of Q is equals to root D and U is equals to -10. So this is the dispersion curve omega K with U is equals to -10. Now A1, A2, and A3 are 3 propagating wave mode. For the propagating wave mode A1, shifting the origin of the opposing current dispersion curve with opposing current to the point A1, and here we can see that the pink dashed curve intersects the blue curve at point B, giving us one triad OA1B. OA1 plus A1B is equals to OB. While for in figure B and C, considering the second A2 and A3 as the propagating wave mode, and this is the sigma curve, and this is the K omega curve with the opposing current. So shifting the origin of the opposing current to the point A2 and A3, here we can see the pink dashed curve intersects the blue curve at 3 points B, C, and D. Similarly here B, C, and D, giving us 3 triads O, A2B, O, A2C, and O, A2D. Similarly here O, A3B, O, A3C, and O, A3D. So here we can see within the blocking limits, we have 7 triads, 1 for the A1 propagating mode, and 3 for the A2 propagating mode, and 3 for the A3 propagating wave mode. So there are 7 triads. Now, considering the case 1.9 root D, here we can see near the secondary blocking, 3 propagating wave mode is there, A1, A2, and A3. Here the blue curve is dk omega u, and the pink dashed curve is also dk omega u, and shifting the origin of the following current to the point A1, A2, and A3. Now for the propagating wave mode A1, we can see both are moving with the following currents, blue curve and pink dashed curve. And the pink curve intersects the blue curve at point B, giving us one triad OA1B. For the propagating wave mode A2 and A3, here we can see the pink dashed curve intersects the blue curve at point B, and similarly for A3, the pink dashed curve intersects the blue curve at point B, giving us one triad OA2B and OA3B. Now we can see within the blocking limit for the following current when both the shifted origin curve and the curve with the origin O are in this are with the following currents. We have only 3 triads. For U is equals to -2 and Q is equals to 1.9 root D for the higher value of the compression and the lower value of the current near the primary blocking. So near the primary blocking, A1, A2 and A3 are the 3 propagating wave mode. Now for the propagating wave mode A, the blue curve is dk omega u, d of k omega u, and the pink dashed curve is k omega with -u. So the pink dashed curve is in the opposing with the opposing current. For the propagating wave mode A1, shifting the origin of the dispersion curve k omega with -u to the point A1, and we can see the pink dashed curve intersects the blue curve at 3 points B, C, and D, giving us 3 triads. Similarly, for the point A2, we have 3 triads B, C, and D, OA2B, OA2C, and OA2D. But for point A3, when we are considering the case near the blocking, we can see only one triad will form OA3B. Here also within the blocking limit, we have 7 triads. Now considering a case of compression with compression is equals to 1.9 root D and U is equals to -2. Here the blue curve is k omega with U and the pink dashed curve is k omega with -u. So 3 propagating wave modes are there, A1, A2 and A3. For the route A1, we can see the pink dashed curve intersects the blue curve at point B, giving us one triad O, A1B. Whereas in the case of A2 and A3, the pink dashed curve intersects the blue curve at 3 points B, C, and D, giving us O, A2B, O, A2C, O, A2D. Similarly here, O, A3B, O, A3C, and O, A3D. So here also near to the secondary blocking within the limit of blocking, we have 7 triads. Conclusion: the formation of triads due to the interaction of flexural gravity waves in the presence of current is studied geometrically. The total number of triads increases with an increase in the compressive force and uniform current. Within the limits of primary and secondary blocking frequency, the number of triads varies between 3 to 7 based on the frequency and the direction of the current. The number of triads decreases within the limit of blocking points when the current is in the direction of the propagating wave. And however, for smaller values of the compression, formation of triad is observed when the current is in the direction of wave motion, which is not present in the case of surface gravity waves in the presence of current. These are my references. Thank you.
Thank you very much, Neha. All right, and that's I've got time for one quick question. Does anyone have a question? I just could ask, have you, this situation where you got seven of these different triads, has that
Yes.
number been observed in other systems, or is that unusually large number?
So in the case of current, we are having only 7 triads. But if we take some other cases, probably there might be like in 2-layer fluid within the flexural gravity waves, within the blocking laminates, we can get more number of triads.
Okay, thank you very much. All right. I think we've come to the end. I'd like to say a few words myself to finish, but let's just thank all the speakers of this session.